Yeah, I'm gonna end up like that. I'm gonna do. I need to stop.
All right. Okay. Hi, everyone. Hello, hello. Hello. Row one. Hi. So hi, yeah. So hopefully you're back from MSE. I hope that you have a few days to catch your breath before, I guess, was it the last midterm? There's probably more. Yeah, okay. All right. Well, after that, there's gonna be a couple of weeks before the exams, so it's all good. So I want to talk about project 2, which is posted. That will involve kind of several interlocking parts. So one is the algorithm part, and one is the C implementation part. But first, what are we actually doing? So the algorithm is called seam carving. So that was published now a while ago in 2007 by Shai Avidan. There's the presentation here. So the goal is to basically intelligently resize images. So kind of get what's on the left, and what the target output is something like what's on the right. So one naive way to go about it would be to just remove columns from the image, right? So that would not be good though, because if you remove like columns from whatever over here, then the person might get distorted, or the person would just disappear. So what you want to do is you want to remove kind of contiguous paths from the top to the bottom, but in such a way that the paths are not crossing anything important in the image. Okay, so the way it would look is like something like this, where the red is what gets removed every time. And what you see is that most of the content is preserved this way. Except, like when kind of at the end, you got to still keep removing if you want to do that. And at that point, the contents get distorted as well. Okay, so that's the goal. And, it's in Photoshop. It's pretty cool. So in order to talk about how to do this, I want to first introduce some terminology. So images in general are, a bunch of pixels, so like small dots on the screen, which have a color. Generally, the coordinate system for images is, like the usual one, but it starts in the top left. So this would be like coordinate 0, 0, and this would be 3, 0. So usually people write it as yx. And this would be y equals 3, x equals 0. Okay, so it's not what you're probably used to, but that's kind of the usual thing that people do for images, and it takes like 30 seconds to get used to. So that's what we're doing. All right. So now that we have the coordinates, so by the way, of course, you might not know, maybe there is no reason to know this, but if you edited photos, you would know. So a pixel is basically a triplet of values. So those are the RGB, red, green, blue values. They can range from anything to anything, but usually, and in the input that we're using for this project, the values range from 0 to 255, right? So let me write it down. and red, green, blue. And intensity ranges from 0 to 255. Out of curiosity, how many people already knew this, or that this is the usual thing? So most people. And then so 0, 0, 0 would be intensity is 040 pixels. So that would be black, right? So the color black, which is arguably not really a color because it's like the lack of any light being reflected, is 0, 0, 0, which means that what's measured is like there is 0 light along red, 0 light along green, 0 light along blue. So one interesting thing, by the way, this is not super computer science related, but color perception might be a little bit different from what you saw in physics class, right? So the way things are usually presented in physics is like, what's color? Yeah. Right. So the wavelength, or like 1 over the wavelength, the frequency of the light waves that are hitting your retina. Is that what you probably see? Like if you look at the seat and you say it's red, it's like a particular frequency? Well, no. So really this red chair reflects, so it absorbs some frequencies, it reflects some frequencies. It's not probably the case, although it could be, that it just reflects this one particular wavelength that corresponds to that exact shade of red. It's more that it reflects more kind of colors in certain areas of the spectrum more than others, and it kind of averages out to this particular shade of red. The perception in our visual system also doesn't measure the frequency of the particular light that's hitting the retina, which would make sense. There's multiple light hitting the retina at multiple frequencies as well, right? So there's, for most people, like there's color blindness and stuff, but for most people, there is several kinds of receptors that are sensitive more to some ranges of frequency than to others. So that's in the retina. What happens with pixels is, every pixel, so everything on the grid, this grid, basically in the same location, you can turn on the green, you can turn on the red, you can turn on the blue. And then because the pixels are so small, everything kind of averages out at the end, and you perceive a particular shade on the spectrum, even though really it's a combination of reds, greens, and blues. Make sense? So one more thing, again, not super relevant to the project, that's on the screen. And what happens on the screen is light is emitted from the screen. What happens if you print the color on the page is the other way. The page doesn't emit anything. The page is illuminated with white light, and then it absorbs some frequency ranges and it reflects some other frequency ranges. And again, for most printers, you would print several colors and then they would absorb some stuff, they would reflect some stuff from the white light, and you'll perceive the reflected light, you'll average it out, it'll be perceived as one particular color that, yes, would theoretically correspond to just one frequency, but in practice is like several frequencies averaged out, several frequency ranges averaged out. Anyways, so not really thinking about that now, we're just thinking about RGB pixels, which, emit red, green, and blue light. All right. So if you don't emit any light along any of RGB, that's black. If you emit the maximum possible amount from red and green and blue, that's perceived as white. And then if you do something like this would be some kind of gray, right? So in general, if R is approximately the same as B is approximately the same as G, the color is perceived as a shade of gray. And what does it mean? It means that light along different frequencies, so specifically the pure R, pure G plus pure B, is emitted at about the same energy. And that means that what you perceive as it's some kind of gray. Like that's what gray means, and that's what white means, is along the entire spectrum, you're emitting light or you're reflecting light. If you're doing something like this, so like whatever, like 10, 200, 10, what does that look like? Yeah, so it's kind of green with like, you know, like not pure green, whatever. What's this? No painters in the room? Well, so the suggestion is cyan. Yeah, so it's kind of green and blue together. That would be kind of something like cyan. So yellow would be something like, yeah, red and green. If you do paint, you'll know that there is two schemes for calculating this kind of stuff. So here we're emitting light. So that means that, yes, like you combine red and green, it's about yellow. And that's what you would get with like watercolor and stuff. So with oil, it would be a little bit different. So, okay. So that's kind of like that. At the same time, for us, those are kind of just numbers. So, okay. So with that information, so suppose that we have, sorry, can we quiet down, please? There's comments in the chat. There's no video. So, all right. So what we will basically have is a color for every pixel. And now what we want is to get at what would a good seam look like, right? So basically, one way to think about it is to say, okay, a good seam, so a good red line like this, basically is along a line where nothing much changes. So where basically the color on the left side of the seam is the same as the color on the right side of the seam. That would indicate that basically you take out the seam and the image would kind of look the same because, you know, it looked the same on the left, it looked the same on the right. You take out the middle, it's not going to change much of anything. So on the other hand, if the seam were to go like through the person, then sometimes you would have like a bright spot on the left and a dark spot on the right or something. So that's the idea. So in order to get at that, we'll compute what's called the energy. This is not really energy. It's just like a term that the authors made up. So the energy is basically how much is the brightness of the image changing if you go from left to right, if you go from top to bottom. If you compute this kind of energy, you'll get this kind of image if you display it. So for every pixel in the input over here, we'll compute the energy. The energy means how much is the intensity going to change if I move one step to the right? How much is the energy going to change if I move one step to the top or the bottom? And the answer is, well, kind of like this. So like if it's bright here, the energy is high. If it's dark, then the energy is low. And it should be intuitive, right? So where there are edges in the image, so where you change from the sky to the hill, yeah, like you move a little bit to the bottom and there is a big change in the brightness, in the intensity. On the other hand, if you're like over here, it doesn't, like if you move one spot to the right or if you move one spot to the bottom, nothing's going to change. And that's what's reflected here. So basically the energy is high where there is rapid change in the image and it's low where there is not. And that corresponds to edges, like what you would call edges in English is also edges in image processing. All right. So what we want is to just formulate an objective. So the objective here is to find a seam that's low energy, meaning a seam where if you go along the seam and you add up all the energies, the sum is as small as possible. So for example, this vertical seam is good because it just goes through pixels with low energy. So pixels where if you move a little bit, nothing much is going to change. Okay. So here's the specific formula for that. So we define Rx as just the intensity of the red at x plus 1 for a particular y minus the intensity for that same y at x minus 1. Right? So x goes horizontally. So basically the difference between neighboring pixels along the intensity of red, aka the partial derivative. Does that make sense? Yes.
Just subtracting like
no, this is just the red.
oh.
Right? So do people see the connection to the partial derivative here? Have you done partial derivatives? Oh, you haven't. Okay. We'll come back to it later. For now, it's just the formula. It is an approximation for the partial derivative. What are you doing if you're not doing partial derivatives? Anyway, it's coming up in about a week and a half, I think. So, okay. So for our N, G, and B, we measure how much at every pixel is red going to change if you move to the right, to the left, or to the bottom, to the top. And then we just add up the squared differences along R and G and B. So delta squared X is going to be high. All right. Yeah, go ahead.
Are we starting at just like how we usually start from? Is it balanced between left or right?
So we are doing it at every pixel, right? So at every pixel, we're computing the energy. That's right. So this is a visualization of what happens where at every pixel, you say the sum of, if I move one pixel to the right, to the left, if I move to the top, to the bottom, display it as bright if the sum is high, display it as dark if that is low. Right? So at every location yx, we compute this delta squared x, we compute the delta squared y, and then we just sum them up, and that is the energy at pixel yx. We compute the energy at every pixel. So if we then display it, so instead of displaying the colors, we display the energy for every coordinate yx, that looks like this. Make sense? Questions about this? So this is kind of just a marketing term, although there is an analogy there. So again, when you do gradients in a week or two in calculus, you'll see that this is kind of an approximation for the gradient. Again, like you can just, for now, just intuitively see, what is going on. For every location, we're saying, if I move a little bit, how much is the color going to change? That's all that we're doing. So, all right. So here's an example. So if you have this 3x4 image, so that's a very small image, and those are the colors, then if you want to measure the energy over here, what you're going to do is you're going to say, okay, so so the difference between 255 and 255 here is that's 0, that's 2, that's whatever, 204. So that means that delta x squared is going to be 0 squared plus 1 squared plus 204 squared, whatever that works out to. Similarly, you'd compute the difference between this and this, this and this, this and this, and that'll give you the energy at this pixel, and it would work out to this. All right. The end result is going to be data that can be displayed like this. So for every pixel, you compute the energy at that pixel, which basically is high if there is an edge, low if there isn't an edge. So, okay. So once we have this kind of thing that's just computed using the formula, then our job is to say, okay, I want to find the minimum energy seam. Right? So a naive way that wouldn't work for a large image to find the minimum energy seam is to just say, I'm going to try and look at all the possible seams, or like all the possible paths through the image, and some of them are seams in the sense that they're contiguous, and some of them jump around, so that doesn't count, because if you try to take like one pixel from the top row, then another pixel from a completely different location in the second row, another pixel in a completely different location in the third row, that would also look ugly. So you don't want that. You want the contiguous path that you take out. So that's why it's called like a seam. So like a seam on kind of an item of clothing or something. So you could try that, but there's too many. So what we want to do is we want to use dynamic programming to actually efficiently find the minimal energy seam. And as it turns out, that's possible. So let's look again at how to do that. So that's what we were talking about last lecture as well. So the idea is like this. I have all those pixels, and I want to find a contiguous path through the pixels. So that means that if I start here, I only ever get to go either here or here or here. And then if I'm here, I get to go maybe here and maybe here and maybe here and so on. and I have a cost that's associated with going through every pixel. So that cost is the energy at that particular pixel, right? So the overall cost of this path is energy here, plus energy here, plus energy here, plus energy here, plus energy here, and so on, right? And just like with painting the houses and stuff, and with selecting coins for change, I don't just get to say, let me get the cheapest one that I can get right now, because it might be that the energy is lower here than here, so it might look like you want to take out this pixel, but if you decide to take out this pixel, then you only then get to take out this one, and they might be extremely high energy, right? So you might like to look ahead. So how do we do that? Again, like this is the inventive step where you have to figure out, okay, if I know how to solve a particular problem, if I know how to solve it for like small instances or for easier examples, can I then use the partial solutions to come up with the final solution? So the sub-problem here is, let's compute the minimal energy path from any top node to node Ji. Okay, so those are like the pixels we refer to as nodes. And I'm saying for this pixel or for this node Ji, I want to know what is the cost of getting from the top to this guy. Okay. And the idea would be that if I know how to get from the top to here, or so I know the minimal cost to get from the top to here, then I can say, okay, so now I know the total cost of getting to here, and the total cost of getting to here, and the total cost of getting to here. Right? So what's the total cost of getting, for example, to here? Well, the only ways to get over here are either to go through this pixel, or to go through this pixel, or to go through this pixel. So the total cost would be the energy here plus the minimum of this guy, or this guy, or this guy. Does that make sense? Because if I am to get from the top to this guy, I have to go through either this one, or this one, or this one. If I already know how much it costs to get here, how much it costs to get here, how much it costs to get here, I know how much it costs to get here, because I'll just take the cost of the current pixel plus the cheapest way to get there. Right? So that's the relationship. I'm saying it's the energy over here plus whatever is the cheapest way to get there, either through here, or through here, or through here. And opt J-1 contains the entire cost of getting from the top, wherever you need to start from the top. You already know by assumption that you've already computed how much it costs to get to J-1 I profit. Once you have that, you can figure out the best cost to get to Ji. So the strategy would be, first compute the opt for the top row. So what's the opt for the top row? Anyone? Yeah.
You're going to choose from the three starting options.
Well, no, so that's the top row, right? So like, what's the total cost of getting from here to here? Well, I mean, it would be the energy of this guy, because like here. But you're just getting charged for this guy, and then for this guy, it's the energy for this guy. Here, it's the energy for this guy, and so on. So once you know the energies for the top row, or the cost of getting from the top row to the top row, you can say, okay, so what's the cheapest cost to get to this guy? And the answer is, well, you're definitely paying for this guy. And then either you'll pay for this guy or for this guy. So it's the smallest of energy here plus energy here, or energy here plus, again, energy here. What's the cost for this guy? Well, it's the smallest of this plus this, or this plus this, or this plus this. So that means that we can if we know the opt for the top row, we can get the costs for, or like the opts rather, for the second row from the top. Once you know the opt for the second row from the top, you can get the opt for the third row from the top, and so on. Eventually, you'll get to the bottom, and you'll compute the opt for this guy and this guy and this guy and so on. And at that point, you can figure out the minimal cost path, the minimal cost seam rather. How do you do that? Yeah.
I mean, you find ops for all the bottoms once you take the minimum.
Exactly. Yeah. So you know the minimal cost to get here from the top, the best cost to get here from the top, and so on. You don't care where you get on the bottom as long as you get to the bottom. So just whatever is the smallest opt for the bottom row, that's the cost of the minimal path. Make sense? Okay. So again, as is usual, this is just the cost for the minimal seam. It's not the same as knowing the minimal seam. However, yes.
So like the way we kind of like when you think about ourselves, but it's kind of obvious what the best one is for just one row. And it's also kind of obvious to get two. And then you kind of figure out for the third, and then you can figure out for the end, and then that's really how we have it.
I mean, that can be a way to make it work. Yeah. So I think like so the way I would usually think, so I mean, I think that could be made to work. So like you're just thinking from the base case and you're saying like, can I figure it out for the base case? And then for the end that's right after the base case, can you figure it out? I think that's a valid way to think about it. Another way to think about it is from the other way. So like, what do I need to know in order to be able to solve for n if I maybe get to solve for n minus 1? Yeah. So I'll give you as much of an explanation as I deem fit after we're done with the algorithm part. All right. Okay, so other questions about the algorithm? So, okay. So I want to give you kind of two techniques that technically we already know well, that you could already kind of see, but that are maybe not obvious. So the first one I want to talk about is n-dimensional tables. So we have this image. So the image looks like this. Sorry, quiet down, please. Sorry, I can't even hear myself. And like, it can't be that the MSE midterm was so interesting that you still need to be discussing it. So, okay. So what we have is this kind of thing. So we need to store it somehow, right? So how do you store this kind of image? So in Python, what you might like to do is something like this, right? So you'd say like whatever, 10, 20, 20, and that would be like 1 pixel, and then another pixel is like this, And then this is like the first row, and then the second row is maybe something like this. So I'll just change it so it's not all the same. And then another row is like this. So something like this. So this would be like a 3x2 image. And you store it, for example, as a list of lists of lists. Right? So then pixel, whatever, 20. So 20 would be this guy. Is whatever, 10, 20, 20. And then to access pixel 20, if this is an image, you would say image 2. So that would give you this sublist. And then you would say add 0. So this would give you this sublist. So to access the G channel, you would say image at 2, at 0, at 1. And that would be, well, this is 20, except the B is also 20. So I'll just change it to 21, and this is 20. Make sense? So you can do something like that in C, but it's inconvenient. So the way we're going to So basically, we're going to use indices to simulate the n-dimensional table. And the way we're going to do it is we're going to say, okay, I'm just going to store all those numbers, but I'm going to store them as just what's called a flat list. So just as a sequence of numbers. So it's going to look something like this. So like 10, 20, 20, and then 50, 20, 15. And then 12, 25, 20, and so on. So if you have Copilot, which you should really try it, then it'll complete it for you. I'll just write it as an ellipsis, right? So now let's say that we want to access pixel 20. So how do we do that? So what we want to do is skip 2 rows, then skip 0 columns, right? So how do we skip 2 rows? We say, okay, so we want to skip 2, and then each row has how many numbers? 6, right? So 3 times 2. Right. So if I want to get to this row, I got to skip 6 times 2 numbers. So those guys. The 6 comes from 3 numbers per pixels and 2 pixels per row. Make sense? So that's going to be 2 times 3 times 2 plus, so 0 columns, so 0 times 3. So this would be the location of the 10. Yeah.
I guess for doing flats, we need to kind of know a bit about the geometry.
Well, yeah, you need to know the size. So this information will encode it as width in a second, right? So then to access the G channel, we need to add 1. And to access the B channel, we need to add 2. So in general, this would be what? So channel K of pixel ij with width W, height you don't really need to know, and number of channels C. So in this case, the channels, that's what you usually call the colors. So there's 3 colors, so 3 numbers per pixel. So what would it be? It would be I times W times C. So the number of entries per row plus J times C plus K. Make sense? So this is kind of everything that you need to know about 2D images, and most images are 2D. So like sometimes, like if you do an MRI or something, the MRI is actually like a 3D image, right? So rather than have just pixels where, you know, the 3D world gets projected on a 2-dimensional image, the MRI would have what's called voxels, where it's a 3-dimensional image, and like in every point in 3D space rather than in any point on a flat 2D space, you know the intensity, right? So like for MRI, CT as well, I guess. But this would generalize. In fact, this in a way is a 3-dimensional table, right? Because you have 1 dimension that's top to bottom and 1 dimension that's left to right. And then you have those channels, which are not dimensions in space, but they might as well have been, right? So really, this is a representation of a 2-dimensional image in the sense that the image itself is flat, but the structure itself is 3-dimensional because you'll also have the color dimension. Yeah, there was a question here. Yeah.
Could you just explain like the generalized case like I am flat? Like how does that read access each channel?
Well, so what we need to do is so if we want to access the ith row and the jth column, right? So the way I think about it is I want to skip I rows. Each row has W times C entries because you have width entries in the table, and then per entry you have C sub entries, right? So this is skipping the first I rows, and then once you've skipped the first I rows, you want to say, okay, like, do I want to start here or do I want to start here? So you want to skip J times C entries here. So if you want to look at the first pixel, you just don't want to skip anything. Want to look at the second pixel, you want to skip 3 entries. So C entries. So in general, this would be J, so kind of number of columns to skip, times number of entries per column. And then here, like if you have, for example, 3 channels, then the first channel is just +0, the second channel is +1, the third channel is +2. All right. So that's kind of the Python implementation, but this is also C syntax, right? So this you can just directly use an array or a block of memory that you allocate, and then you can store whatever you want with whatever dimension. So there is a way to use built-in multi-dimensional arrays in C. I absolutely do not recommend it. Nobody does it. Nobody should do it because it's very annoying and stupid. So like ill-advised is what I want to say. We will be using that for the project. Yeah.
You recommend like us implementing a function that does it easily, like get out and then makes the stats right.
I don't so much recommend it as I actually provide a function that does it.
So I guess you're
Yeah. Okay, all right. That's as much time as we have today. So we'll continue tomorrow. See ya. Bye.